Okay, it's working now. All right, we can use the percent by mass composition. Sometimes you can find percent, you could figure it out if you know the formula. But sometimes you can find percent mass composition on sites like, for example, aluminum chlorate. Aluminum chlorate, they're saying is 38.35% chlorine. And so let's take a look at aluminum chlorate. So if we just look, do a search, we go to maybe Wikipedia for aluminum chlorate. Oftentimes what you'll find is the formula. Wikipedia, the values there are pretty at least the physical data that they give is pretty good. That's chlorate, it's aluminum chlorate. Oh, they might not have it. What's the formula for aluminum chlorate? Yeah. Okay, it's going to be Al. Okay, chlorate is, what is it? How many oxygens is chlorate? 3. And the charge? -1. So we'll need 3 of those. So it'll be AlClO3, 3. Let's see if they have it. Actually, they don't have it. So we don't have the data, but oftentimes what you'll see is the data here. If we do a search, MSDS, you know what MSDS stands for? Or SDS? MSDS is the old word. It's Material Safety Data Sheet, but now they just call them Safety Data Sheets. SDS. We'll just plug in aluminum chlorate in here. ClO3, taken 3. See if we have it. Chlorate, SDS. This might not have it. But sometimes what they'll do is, if you have the SDS or the MSDS, they'll give you the percent. They'll give you the formula like this, and then they'll give you the percent compositions. List them. It's this much percent aluminum, this much percent chlorine by mass. And so that way you can find these things quickly, but unfortunately it's not here online, so we are just going to take their number here and use it. And so aluminum chloride is 38.35% chloride. We could say, is it really chloride? Is that really chloride? It turns out the answer is actually no. It's not chloride. What is chloride? Chloride is Cl minus. Chlorate is ClO3 -1. Now, the way we visualize this is a bit like this. We don't break it up into ions. The one way of visualizing it is this, for the chemical properties. I might consider each oxygen as a 2- here. And that means the chlorine must be what in order to go to -1? +5. And so 2, 4, 6, that means chlorine must be in the 5, what we call the 5 oxidation state. Chlorine's oxidation state varies. And when we look at it on the periodic table, and can somebody remind me what oxidation state is? Well, it could be losing electrons, but it doesn't have to. It could gain electrons and still have an oxidation state, because oxidation state is defined as chapter was that? Chapter 6? nobody remember seeing oxidation state? I've been using that number quite a lot. Okay, this is, let's see, binary, molecular compound. It's in here in the PowerPoints for chapter 6. I spent a couple of minutes talking about that I didn't like the way. Does anybody remember when I said I didn't like the way they defined it in the PowerPoint? No? I gave an example too. Yeah, I didn't like the way they defined it on the PowerPoint. If anybody remembers, it's in one of the videos. But anyway, the oxidation state for chlorine can vary. If we look at the periodic table, it can vary from what to what. Can somebody tell me what chlorine? So maximum positive charges and negative charges based on its position in the periodic table. Positive 7, good, is the max positive charge, and the negative charge would be -1. And so the charge ranges from, basically from -1 to +7. Here, the chlorine is in the +5. And so this chloride is in the -1. That charge, because chemists are most interested in electrical interactions, that charge makes a huge difference in the behavior of these two. In fact, the chemical properties are significantly different because of this. In fact, they're totally kind of opposites. We have things called oxidizers. We talked about oxidizers. What do oxidizers do? Take electrons. Right? Chloride is not an oxidizer, but chlorate is. Chlorate's an oxidizer because who do you think takes the electrons? Not the oxygens. The oxygens are already heavy because oxygen likes to be -2. So who do you think takes the electrons? Chlorine, because is +5? +5, what's your feeling about +5 or +7? My feeling is that's a lot of electrons to lose. A lot. And so, it makes it more electron hungry, in that sense. And so these two are totally different. Chloride and chlorine and chlorate are totally different chlorines. And they behave totally differently. And so we like to pay attention to the charge. This is why I'm bringing up the charge ahead of time, because I like to pay attention to that. So I don't like this slide, for one. Aluminum chlorate is 38.35% chlorine. Chlorine is just Cl, there's Cl. We don't call that chloride, and oxygens are all 0. Not like that. So there's chlorine and oxygen are the two elements that make up chlorate, the ion. So this is another slide I don't like, but these are the slides I just take out of the book. I don't modify them because what happens is this, typically they're, in any textbook, depends on how many revisions it undergoes, but typically there are a lot of errors. They normally print errata tables for textbooks. So sometimes the answers are wrong, sometimes, things need to be verified. And so this is typical for books. So we try to find the errors. Well, this would be an error. What mass of aluminum chloride is needed as a source for 50.0 milligrams of chlorine? And so I would never write it chloride. And so if we want 50.0 milligrams, 50.0 milligrams of chlorine. Now, how should I say chlorine? Should I say Cl2 or just Cl? Now I'm calling it chlorine. Should I say Cl2 or Cl? if I say Cl2, because chlorine's ambiguous. Chlorine can either refer to chlorine atoms or it can refer to chlorine molecules. What do you think I'm talking about when I'm talking about chlorate? Am I talking about chlorine molecules? Chlorine's a green gas. And so trapped in chlorate, you know, we talked about things getting trapped in crystal structures. For example, getting trapped in a lattice, you might have waters getting trapped and would form hydrates, hydrated crystals. But is there green gas trapped in the chlorate ion? So let's look at a common chlorate. This is a chlorate you're going to use in the lab. It's KClO3. It's called potassium chlorate. And so let's take a look at what potassium chlorate looks like. This is what potassium chlorate looks like. Is there green chlorine gas trapped in the crystal there? Maybe if we heat it up, we might drive off the green chlorine gas. But what do you suspect? There's no gas trapped in there, and so it's not chlorine. You know, if you look at the chlorine is this is chlorine here. This is what we call lone pair. We'll talk about these later. But we have 3 oxygens attached to this chlorine here. This shows its structure a little bit. So this is a chlorate ion. This is a potassium ion. So we got the ions. We form an ionic lattice. Just packing together the ions. But do you see Cl2 in the ion? Do we see any Cl2? No, I see chlorine atoms and I see oxygen atoms. And so when we do this, we want 50.0 milligrams of chlorine atoms. This goes the same thing with the chlorinating agent. When we're talking about the chlorinating agent before, you know, the typical chlorinating agent is sodium hypochlorite or bleach. Bleach is very common, NaClO. And when I look at the bleach, ClO, this is it on the, these are brand name Clorox bleach. This is sodium hypochlorite here, it's an ionic compound as well. This is a hypochlorite ion. But, you know, when they're talking about chlorinating agents, they just want chlorine inside the pool. Because the chlorine here, what do you think the charge on the chlorine here is? You know, it turns out that like chloride would make an awful, like say, hey, you know, I need to chlorinate my swimming pool. I ran out of chlorinating agent. I'm just going to go get a jar of table salt and dump it into the pool, and then I'll get my chlorine, right? So if you get a jar of table salt and dump it into the pool, is that a good, adequate substitute? I need 1 ppm chlorine. I'm going to dump in 1 ppm chloride in the pool and be done with it. You think that'll work? In other words, what would you rather sprinkle on your French fries? Would you rather sprinkle some salt, table salt, or would you rather sprinkle some bleach on your French fries? Both of them have chloride, right? And sodium hypochlorite. So I got my sodium and I got my chloride. I got my sodium and I got my chloride, so I could just use bleach instead of, well, this is not chloride, is it? This is totally not chloride. This is chlorine, and in fact, if I look at hypochlorite is ClO minus. If we treat oxygen as 2 minus, what's the charge on chlorine? What's the charge on chlorine? +1. And so basically, our Roman numeral 1, whatever we want to do. You know, these don't split up into ions, but basically it's this. If I want to bleach my pool, what would be a more powerful bleach? Chlorate or hypochlorite? Okay, what bleach is an oxidizer. Bleaches are oxidizers, like chlorine. Chlorine's an oxidizer. We want to take electrons. Chloride is not a great oxidizer. Chloride's not a great oxidizer because it already has an electron. How many electrons does chlorine want? How many electrons does chlorine want? It wants 1 electron. Well, it has 1 electron here, 1 extra electron. It made chloride. Same thing with fluorine, makes fluoride. bromine makes bromide, iodide comes from iodine. Now, over here, you take a look, which one of these do you think wants more electrons? The oxygen's already happy. How many electrons does oxygen want? We look at the periodic table, oxygen wants, well, you know, basically it's this. All these want how many electrons? They get a -1 charge, so they all want 1 electron. They have an extra electron. All these want 2 electrons. These want 3 electrons. These want 4 electrons. And so oxygen wants 2 electrons. When we look at oxygen over here, how many electrons does it have? 2. 2 electrons. And that means that if oxygen doesn't want the electrons, who's taking the electrons? Who's taking the electrons would be chlorine. These are both bleaching agents here. Chlorate and hypochlorite are both bleaching agents. And which one do you think wants electrons more? Chlorine with a +5 deficit of electrons, or chlorine with a +1 deficit of electrons? With the +5. And so this is going to be a much more powerful bleaching agent than this. If we were to use this stuff, we'd probably go less than 1 ppm. This is going to be more powerful. And so all this charge stuff is really important for understanding the we need to correlate this with stuff. And so I'm trying to start with the correlation now. We're looking at charge. Charge is very important. And so to call the chlorine and chloride is, to me, a gross error. Just like what I said earlier, to call the oxidation state the charge is a gross error too, potentially. And that's the slide that bothered me earlier. But, you know, no book is perfect. So people will say, well, why don't you change the book? Or why don't we have print out a errata sheet? Well, they update the edition, so don't always catch all the mistakes. But anyway, let's go on with this. And then this is also good because these are from the publisher, these PowerPoints, so you can see just exactly what's happening. So 50.0 milligrams of chlorine, and it's 38.35% by mass. And so it's 38.35 parts out of 100 parts. Now what mass units can we use for this? Is this restricted only to grams, or can I use any units I want? Turns out I can use any units I want. I could put in pounds, 38.35 pounds per 100 pounds. Whatever mass, 38.35 grams per 100 grams. But since I already have milligrams here, I'm just going to use milligrams. And so 38.35 milligrams of what? Per 100 milligrams of what? Of chlorine. And so if you don't, if you're not certain, you could just write it out, chlorine. This is what I did when we were doing the pool problem, because I didn't want to talk about this at that time. So if you look at all the dimensional analysis problems we did with the pool, I wrote it out completely. That's chlorine per 100 milligrams of aluminum chlorate. Aluminum chlorate is AlClO33. And so we want 50.0 milligrams of chlorine, so we need to cancel out that chlorine. So it's going to be 38.35 milligrams of chlorine for every 100 milligrams of aluminum chlorate. This would be like saying this could be a, what this could be? This could be a chlorinating agent for a swimming pool. In this particular chlorinating agent, we have a lot of chlorine. This is 38.35% chlorine. What was the chlorinating agent that we used for the swimming pool? It was like 7%. That's because it was a mixture of water and chlorinating agent. This is just pure chlorinating agent here, if we wanted to. We probably don't want aluminum in the pool. Okay, and then just calculate it out. So let's see what they did here. So they used the milligrams here. And how many sig figs are we allowed for this calculation? 3. So the other thing you have to realize is that these books have multiple authors. And the books that have multiple authors, each person has their own way of doing things. And so the person who solved this does it like the way I like to do it. They like to show the number before rounding and the number after rounding. And then you have a whole bunch of people who don't show the number before rounding, they just show the rounded number. And so it's not consistent, the book's not consistent, but that's often the case. Because especially with the homework, many different people are involved in solving the problems. All right, 130.37 milligrams of aluminum chloride. And then to round it to the proper number of sig figs, we're allowed 3, so 1.30 times 10 squared milligrams, or 130 milligrams of aluminum chloride. So we did percentage composition by mass. I started with that, and so I'm going to skip these slides here. We did calcium fluoride. Now we're going to talk about our formulas, empirical formulas. Empirical formulas, this is the lowest ratio, that is the simplest whole number ratio. And so empirical formulas, they give you less information. So for example, this is hydrogen peroxide. Hydrogen peroxide. Peroxide, what's the formula for peroxide? O2. O2. 2 minus. That's peroxide. This can't be hydrogen oxide, because if this were oxide, then each hydrogen must be 2 plus. 2 plus is not possible. 2 plus charge on hydrogen is impossible. It's impossible because hydrogen only has 1 proton and 1 electron. And so if we lose that 1 electron, it's only electron, then it's plus 1. There's no way to make it plus 2. And so a 2 plus charge on hydrogen is impossible. And therefore this has got to be hydrogen peroxide, because then it works. So plus 1 charge on that is good. Hydrogen peroxide is typically thought of as an oxidizer or a reducer. Do you know about hydrogen peroxide? What does oxygen like? How many electrons does oxygen like? 2. How many? This is why I didn't like that slide earlier. If anybody remembers, which nobody does, but if anybody did remember, the reason I didn't like the slide earlier is because they said that the oxidation state is the same as the charge. When I look at the charge here, the charge is -2, but the oxidation state is not -2. I've already had a couple of questions about this earlier. What is the oxidation state on oxygen here? And so what I said during the, when we're talking about chapter 6, is I said that the oxidation state, and this is, the oxidation state is the charge on an individual atom, not the charge. The charge can be the charge on an individual atom, or it could be the charge on the ion, the total ion. We have polyatomic ions. I understand why they did it, because they did, now I remember where it is. It's when they were talking about monatomic ions. Let me put that. And show you what I'm talking about. Monatomic. Wow. Somewhere in there is it. I give up looking for it, but basically we have 2 oxygens. there. Each oxygen must have a charge of, we have 2 oxygens there, so each oxygen must have a charge of -2 or -1. Each oxygen has a charge of minus, and we have 2 of those, so those 2 combined will give us a charge of -2. So the charge is -2, but the oxidation state is -1. Now the question, the student came up to me and asked me this, you know, why is this called mercury 1, not mercury 2? Because the charge is 2, so what, shouldn't it be called mercury 2, not mercury 1? Because we're looking, mercury 1 refers to the oxidation state, not the charge. The oxidation state of mercury is, each mercury must be +1. And we have 2 of them, so it gives a charge of +2. Okay. So anyway, what does oxygen like to be? Does oxygen like to be -1? Or does oxygen like to be -2? -2, it's fixed charge, -2. And so that means hydrogen peroxide is an oxidizer, because it wants electrons. Things like chlorine, what does chlorine like to be? -1. That means chlorate, perchlorate, chlorite, and hypochlorite are all oxidizers. Those are all oxidizers. 1, 2. Well, okay, this is a molecular formula. The molecule of hydrogen peroxide looks like this. It has a hydrogen and then 2 oxygens and then the hydrogen. This is the molecule of hydrogen peroxide. But the empirical formula is this. The empirical formula, this is not the simplest whole number ratio. The empirical formula is the simplest whole number ratio. And the empirical formula is 1:1, HO. And so what you have to do is you cut the molecule in half, but if you cut the molecule in half, it's no longer hydrogen peroxide. And so the empirical formula, we lose structural information. The molecular formula is much better. This is the molecular formula. And so empirical formulas, if we have a choice, you want the empirical formula, you want the molecular, we want the molecular formula because it tells us what the molecule is. So for example here, C4H10 is the molecular formula. This is molecule of this. How do I know it's a molecule? How do I know it's a molecule? Yeah, 2 nonmetals. So this is C4H10. It's like butane. There's a certain, we could name this 2 ways. You could name this by our normal rules. Our normal rules are usually for what we call inorganic compounds. When we deal with organic compounds, organic chemists have a whole different set of rules that they use. The rules that organic chemists do is they look at how many carbon atoms there are in a chain. And so this has a chain of 4 carbon atoms. That chain of 4 carbon atoms, they give the parent or the base name but. And then they look at the bonding and the structure. So this would be called butane. And so organic chemists will have their own system. We would name this tetracarbon decahydride. But nobody would recognize it because it has a totally different. And so, how do I know it's an organic compound? Carbon and hydrogen. You know, most of the other ones we were looking at, nitrous oxide, dinitrogen monoxide, those are inorganic because they don't contain any carbon. And so the empirical formula for this would be C2H5, but that's like half the molecule. We don't want half the molecule, we want the full molecule. Like this, hydrogen peroxide, you're going to cut out half the molecule and call it that? No. If you cut out half the molecule, it's no longer hydrogen peroxide. So the empirical doesn't give us as much information. Some things we just need the empirical formula for. For example, salt lattices or ionic lattices, they can be huge with lots. If you just look at table salt, or even KClO3, see if there's a lattice here, KCl 3, it gives us a lattice picture. So we can see, this is KCl3. Here we want to use the empirical formula. Because do you want to count how many chlorides we have and then how many potassiums we have? No, I don't want to count those. We'll just use the empirical. We'll just and not only that, we can have any size crystal we want, right? Because it doesn't form discrete molecules. Anything that doesn't form discrete molecules, we use the empirical formula for because it's too much hassle to count exactly how many potassium ions and how many chloride ions there are in a lattice like that. And do you see, is this potassium paired with this chloride, or paired with that chloride, or that chloride, or that chloride? Which chloride is it paired with? All of them, actually. There's no discrete unit there. This is like, think about ionic lattice like this. If you're positively charged, right, then all the negatively charged species are going to be drawn to positively charged species, and vice versa. And so if you're positively charged, you want to be surrounded by as many negative species as possible. Well, how many negative species can you fit? Well, you can fit them all around you this way and then put one on top and one underneath. And then you're completely surrounded by negative species, and that's going to make you happy. And likewise, and so if you're a positive species, you try to surround yourself with as many negative species as possible. And if you're a negative species, you try to surround yourself with as many positive. And this is what a lattice is. An ionic lattice is all about. There's no one pair because you want to surround with a max, the max that can fit in there. And so for anything that doesn't form molecules, we prefer empirical. For anything that forms molecules, we definitely prefer molecular formula. Sometimes we're stuck with the empirical formula. Sometimes we're stuck with the empirical formula. Ignore this slide right now. We're going to go. So we're stuck with the empirical formula because this is what happens when we do chemical analysis. When you do chemical analysis, one, how are formulas determined? Yeah, and what kinds of experiments will tell us the formula? So for example, the formula for water is what? H2O. Well, where did that come from? What observation did that come from? How do you know it's H2O? The thing is, you've been taking people's word for it, right? But what proof do you have that it is H2O? Well, I want to know, what scientific theory is that? I need, when I'm asking for proof, I need some kind of, substantial proof. I don't want, it's somebody did the experiment, some guy or some girl did some experiment a long time ago and figured it out. I don't know the details, but what proof do you have? Do you have some proof? Okay, it boils down to this. Well, how do you know the composition of this? It's not so easy, actually, because let's say you're trying to make a new drug, and you want to figure out, well, this stuff works pretty good. What is it? Well, what is it? We want to know what? We want to know its composition, and we want to know its structure. Right? And the people, there's some things happen serendipitously, like penicillin. Did you hear about penicillin, the discovery of penicillin? The discovery of penicillin happened because this is the story I know, is that there's bacteria cultures that were left over the weekend. They didn't bother cleaning on Friday. It's a good thing they didn't bother cleaning because they left them out, and when they returned on Monday, I guess all the bacteria was dead. And so they tried to figure out what killed it. So there was a hunt for a molecule, and that molecule turned out to be penicillin. But how did they figure out what the composition of penicillin is and what the structure of penicillin is? Obviously, you could look it up in a book, or you could be told, H2O is H2O. Well, if somebody asked you to prove it, could you prove it to them? You might think, oh, that's a ridiculous request because everybody knows H2O is H2O, but that's not such a ridiculous request for something new, some new antibiotic. It's not such a ridiculous request for anti-tumor. The same thing happened there in Michigan, University of Michigan. They're trying to see what happens with electrical fields and tumor cells. So they put some probes in there, and it ended up killing the tumors, but not the electric field. The probes that they stuck in there were made out of platinum, and they saw that the platinum was starting to react with the culture medium, and whatever it was forming was killing the tumor cells. And so they had to find out what that particular, well, they knew it must contain platinum, but what's the composition of that anti-tumor agent? And so after a long, arduous process, they finally figured out the composition and the structure. It turned out it was 1 platinum, 2 chlorines, and 2 ammonias kind of stuck on there. And that was a powerful, and then this drug is still being used today. It's a powerful anti-tumor chemotherapy, they call it, chemotherapy agent. But the thing is, how do they figure out, what the composition and the structure is? So what we're interested in is composition. And so here is a perfect example, a pure compound. Well, if we want the composition of mixture, we can try to get it. But typically we want the composition of pure compound. Let's say this has been purified, this liquid. What is the composition of this liquid? And so what they're saying here is a sample of a pure compound. Okay, well, where did that number come from? Is made up of 1.61 grams of phosphorus and 2.98 grams of fluorine. And so where that came from is this. We take let's say we take an unknown substance. When I say unknown substance, what I'm talking about there is it's either going to be an element or a compound. It's not going to be a mixture. And so what we can do is this. We can take a mixture like that, and then we can do separations. Now, if we have a mixture and we want to separate it into substances, can we use physical separation techniques, or do we have to use chemical separation techniques? You could use both, but probably don't want to use chemical too much, because what will happen with chemical? If I'm trying to identify an unknown substance and I use a chemical separation technique, what's going to happen to that unknown substance? What happens in a chemical separation? What happens in a chemical change? It changes its identity. It changes its. This is from week 1, so this should be like hopefully this is like, as we progress, it should be more and more like kindergarten. If you go back to kindergarten and you look at the math you were doing in kindergarten, it should be like that. Ideally, on a quarter system. Quarter system is 10 weeks long, and so when you're on a quarter system like at UC, except for Berkeley, Berkeley's on semester system. And when you're on a quarter system at UC, then we're already halfway through, right? Or more than halfway through. That first week stuff should be like kindergarten. That's the way, that should be your goal if you transfer to a quarter system. You should have that as a goal. But anyway, we got to use physical separation techniques. We use physical separation techniques, and we can separate it into different substances. And so let's say one of the substances is unknown. We know it's pure, so that's why they're saying pure. Pure compound. Okay, then what happens is you send it out for analysis. And there are a whole bunch of chemical analysis techniques. We're going to talk about one. in this chapter near the end. But basically, there are analysis labs. Like I was trying to make some new stuff, and I actually sent it to a lab in Gardena, and they have a whole bunch of instruments that can determine the composition. And so when you send it out for analysis, you're either going to get the mass composition or percent mass composition. In this case, we get the mass composition. So in this particular problem, you send out a sample, it comes back as 1.61 grams of phosphorus and 2.98 grams of fluorine. Now they're saying this is a compound, they're saying it contains 2.98 grams of fluorine. Is that F2 or F? It's a compound. The F2 or F? Yeah, it'd be F. Think about this. Water contains oxygen, correct? Or water contains oxygen. Is that O2 or is that O? It's O. It's not O2. You know, you can't breathe the water. We breathe O2, but we aren't going to breathe water. Toothpaste, depends on the toothpaste you have. Toothpaste contains fluorine, a certain percentage fluorine. Is that F2 or F? It would be F. I just looked at the toothpaste this morning. Sodium fluoride is common. So fluorine is fluoride. And the fluorine, we usually use it generically. And so this is it. Only two elements, so the total mass, we just added up. That's 9, 15, 4.59 grams total. All right, let's see how they do it. So what we do is we send it out for analysis, chemical, we call it chemical analysis. And you know, you might do a chemical analysis. You use different, like if you're analyzing phosphorus, there's certain ways you analyze for phosphorus. If you're analyzing fluorine, it's different. You know, there are different ways. But this is a realm of analytical chemistry where they try to find out what's in it and how much of it. And so now we have it, but is a chemical formula a mass ratio or is a chemical formula an atom ratio? It's an atom ratio. And so we don't want the mass ratio. I know what the mass ratio is, 1.61 grams of fluorine for every 2.98 grams of fluorine. That's not what I want though. So, what we have is something like this. I'm going to use their table here. So the element, we have phosphorus and fluorine. And then we have the grams. Okay, there could be one more here, percent mass composition. But here we can skip it because the next step is to figure out the mass. And since we're already given the mass, we don't have to do this particular step. And so if I don't have to do this particular, I'm just going to skip this one and go straight to this. Although I can calculate the percent by mass composition. I'll take 1.61 divided by 4.59 times 100% for phosphorus, and then 2.98 divided by 4.59 times 100% for the percent fluorine. But let's skip that, and we're going to go to 2.98 grams of fluorine. Now, when I work with this, like H2O, this is an atom ratio. And so how many atoms of hydrogen? 2 atoms of hydrogen and 1 atom of oxygen. This could also be a dozen ratio. So for example, if I had 2 dozen hydrogen, how many dozen oxygens do I have? I'd have 1 dozen oxygens. So it could be an atom ratio, it could be a dozen ratio, or it could be a mole ratio. If I have 2 moles of hydrogen, how many moles of oxygen would I have? 1 mole. And so typically we call it an atom ratio or a mole ratio. A dozen isn't so useful. Now, the situation is, if we're given U, I would do atom ratio. But if we're given grams, I don't want to hassle with gram to U conversion and then figuring out how many atoms I have. I just am going to go straight from grams to moles. And so if I got grams, I'm just going to go to moles. Well, how do I go to moles? Well, I need the molar mass. And the molar mass of phosphorus, we can just get off the periodic tables. Let's just take a look at phosphorus. It's 30.974. If it's 30.974, then I'm going to use what? I'm going to just say 1 mole of phosphorus is 30.97 grams of phosphorus. And so how many moles is that going to be? So 1.61. 1.61 divided by 30.97. So this is 0.05198. How many sig figs am I allowed? 3. And so I'm going to carry 1 extra, at least 1 extra. 0.05198 mole of phosphorus. Okay, now I'm going to do the same thing for fluorine. A mole of fluorine from yesterday weighs 19.00 grams. So there's going to be 2.98 divided by 19. This is going to give me 0.156 moles. Now, a chemical formula is an atom ratio or a mole ratio. It's an atom or mole ratio. That's what a chemical formula is. So what I'm going to do is I'm just going to get the mole ratio. Formula. Mole ratio. And so then it's pretty easy. It's the mole ratio is P 0.05198, F 0.1568. Does that look like a proper formula to you? No, it's bad. And so what we need to do is we need to simplify this. Because what we want are whole numbers. You know, we can't have fractions of atoms. And so what we're going to do is we're going to simplify it. The easiest way to simplify it is by dividing by the smallest number. So simplify by dividing by smallest number. And so I'm going to go over here and do P 0.05198 divided by 0.05198. F 0.1568. 0.1568 divided by 0.15. No, that's wrong. Divided by the smallest number, 0.05198. So this is going to give me P 1.0000 F. So I got to use my calculator here. At F 3.017. You remember the law of multiple proportions, right? What did the law of multiple proportions say? Whole number ratios. And so, should I do this? For every 100 phosphorus, there are 302 fluorines? Does that sound right? No. What do you think this might be attributable to? That's probably due to round off error. And I didn't carry all the digits in the calculator. Not only that, when you do these, when you send it out for chemical analysis, do you think they're perfect, error-free? No, there's going to be errors there. So typically what we'd say is, well, this seems close enough to, actually, how many sig figs? I'm only allowed three sig figs, sorry. This is close enough to PF3. PF3. And so PF3 is what we call the empirical formula. PF3. When we do chemical analysis, this is all we can get. We don't know if the molecule, the empirical formula is not the best. We want the molecular formula. And so we shouldn't stop here. We need one more. If applicable. Well, PF3 forms molecule. And so is this half a molecule, a quarter of a molecule? What is this? And so an extra step required. To get molecular formula, we have to do one extra step. And the extra step is this. Do you know we can weigh molecules? Just like weighing atoms, we can weigh molecules. What instrument can we use to weigh atoms? Mass spectrometer. What instrument can we use to weigh molecules? Mass spectrometer. In fact, the same instrument can be used to weigh atoms or molecules. And so if we use a mass spectrometer, we can figure out how much a molecule of this weighs, and then see. And so what we do is we need to compare the empirical mass. The empirical mass is how much this empirical unit weighs, 1 phosphorus, 3 fluorines, with molecular mass. If the empirical mass and the molecular mass are the same thing, that is, you shoot a molecule through your mass spectrometer and it weighs the same as the empirical mass, then they're the same thing. But what can happen is this. The molecule might weigh twice as much. If the molecule weighs twice as much, then there are actually 2 phosphorus and 6 fluorines there. Or a molecule might weigh 3 times as much. If it weighs 3 times as much, then there are actually 3 phosphorus and 9 fluorines in the molecule, intact. We don't have to cut it. And so we need an extra step there. We need to know how much a molecule weighs. All right, so they got this. Actually, I skip that. No, so they got the moles, and then they get the mole ratio. How do they get the mole ratio? The easiest way is just divide by the smaller. Sometimes you have to do an additional step. When we simplify, step 1 is divide, and step 2 is multiply by factor, if necessary. In this case, it's not necessary, but what can happen is this. We might come up with a situation where we get A, B, 1.5. Now you think, okay, 1.5, yeah, that's round off error. 1.5, round off error, I'm just going to round it to 2. But do you think you're going to have that significant round-off error? Round-off error should be kind of small, right? And so in this situation here, the best thing to do is multiply it by a factor. We multiply it times 2. And so we come up with A2B3. Or another scenario might be, let's say I got A1.33B. In this case, I probably want to multiply it by, I got 1 1/3 and 1. So if I have 1 1/3, I probably want to multiply by 3. Yeah, good, times 3. And so if I times it by 3, then 1 1/3 is how many thirds? 4 thirds. And so it's going to come out A4B3. You see that? Because this one we probably don't want to round down. I mean, if it was a 1/3, it's kind of harsh to round it down. This one we probably don't want to round it up. I mean, it's halfway. We don't want to round it up because this is going to be a pretty big round off there. But in this case, it's not necessary. In this case, it was fine. And so here's a case. Well, nicotine. We already know what nicotine is. Nicotine contains. Okay, let's say this was unknown. Let's say we're thinking. We have a sample. We think it's nicotine. We send it out for analysis. The analysis comes back. In this case, the analysis comes back as percent mass compositions rather than masses. That's okay. We have to do one extra step here. The one extra step here is this. In order to get the masses from percent mass composition, we make the assumption. We assume we have a 100-gram sample. And we can get it easily. And so I'm going to stop here. We'll take a break and then I'll start this problem.